Hello and welcome to today's revision session on atomic structure for GCSE Separate Science Physics. So in the first part of this revision session we're going to look at the structure of the atom. Now Democritus originally postulated that all atoms were indivisible balls, which we call the atomic model, but by the end of the 19th century we realised this model was not correct. So it was realised that atoms were not indivisible spheres and had a structure inside of them, which we call the subatomic structure. Now this model was later experimentally confirmed by Ernest Rutherford in 1911 in an experiment called Rutherford's scattering experiment. Now it was determined that an atom had three smaller particles inside of it: the proton, a positively charged particle found in the nucleus with a relative mass of 1, the neutron, a neutral particle found in the nucleus with a relative mass of 1, and the electron, a negatively charged particle found in the energy levels around the nucleus which has a relative mass of 0 and is fundamental, which cannot be broken down further. So you should be able to understand your proton, your neutron and your electron. Now protons and neutrons are made from something smaller, whilst the electrons are fundamental, they cannot be broken up. Now the proton and the neutron are of similar size, but the electron is much smaller than the proton and the neutron. Now we consider all of the atomic mass to be in the nucleus. We assume the electrons have no effective mass. So we can summarise the properties of the subatomic particles as the following. Now it was determined that if you change either number of protons, neutrons or electrons in an atom, you change the different type of atom that you have. So the number of protons in an atom determines the element. Each element has a different number of protons. So if you change the number of protons, you change the type of element. The number of neutrons in an atom determines the isotope. Each different isotope has a different number of neutrons. So if you change the number of neutrons without changing the number of protons, you change the type of isotope. Whilst the number of electrons in an atom determines the ion. Each different ion has a different number of electrons. So if you change the number of electrons without changing protons, you change the type of ion. Now when the proton number is altered, this takes precedence over all other changes. So if you ever change the proton number in an atom, it becomes a new element. A new isotope can only occur if there is no change in proton number, which is also the same for an ion. Now protons and neutrons are found in the nucleus, so the nucleus is very massive and dense. The electrons are found in energy levels around the nucleus. Electrons do not orbit the nucleus, they exist in levels. Now different names for levels can be states, orbitals or shells. The name for the shell nearest nucleus is the ground state, and the shell furthest away from the nucleus the valence state. Now most of the atom is empty space between the nucleus and the energy levels. The radius of the nucleus is about 10,000 times smaller than the radius of the atom. So this picture on the screen is not to scale. So we can summarize the properties of the subatomic particles in the following slide. So you should be able to know the relative charge and relative mass of each particles and what happens to the atom if you change the number of protons, neutrons or electrons. So the next thing to consider is mass number, atomic number and isotopes. Now the periodic table is very useful in physics, as it can tell a physicist how many of each subatomic particle is in an atom. So when looking at the elements in the periodic table, this information is displayed as the following. Now the bigger number is always the atomic mass, or the mass number, which is the number of protons and neutrons. Now the atomic number or proton number is the smaller number, which is the number of protons. Now as every atom is neutrally charged, the number of electrons equals the number of protons for an atom. So all atoms have to be electrically neutral, so the charge of protons and electrons cancel each other out. So in this atom there are 3 protons, 3 electrons but 4 neutrons, because you're doing 7 minus 3 to work out the number of neutrons. So here's an example of a nucleotide notation. So there are 15 protons and neutrons in the atom, there are 7 protons in this atom, so there are 7 electrons in the atom as well. So it means the number of neutrons is 15 minus 7, which equals 8. So the number of protons is unique to every element in the universe. If this number changes, the atom becomes a different element. So if this takes place, we call that transmutation. Now this is why we believe we've discovered all of the lighter elements in the universe, as the bottom number in the periodic table increases by 1 by each element. So this means in standard atoms the number of electrons in an atom increases by 1 per element. So that each energy level except the first one could only contain 8 electrons, and those facts all combine to form the theory of periodicity, which explains all of chemistry and a small part of physics. The next part we're going to look at is the development of the model of the atom. So to explain the atom and what it's made from, we come up with a scientific model, and the concept of a scientific model is is extremely important. It is an idea or theory which is used to explain observations and data made in experiments. So there's been many models of the atom, from Dalton's atomic model of the atom, to Thomson's plum pudding model of the atom, to Rutherford's planetary model of the atom, to Bohr's energy level model of the atom. Now, it's important in science how we continually update our scientific models with the latest experimental data. So in the future we may make further amendments to the model of the atom. Now, the scientific method is the pathway we use in physics to update our models and ensure their accuracy according to the experimental results we achieve. So the scientific method is as follows. Step 1. Theorize a testable model or idea. Then gain experimental values about the model and idea. Then alter the model and idea to explain the experimental values, and then repeat steps 1 to 3. Now, this is the pathway we use to update our model of the atom, and the idea Rutherford used when he worked out what his model of the atom was going to be. Now, the model of the atom is still being updated in the present day, so in science our model must be able to explain the observations that we make, and if the model does not follow the observations, we must replace it with a model that does. So this means over years of discovery we can change our scientific models, which is what has happened with the atom. So the first model came from a chemist, John Dalton, who theorized that atoms were indestructible and indivisible. Now, in 1897 the electron was discovered and found to be inside atoms. This means we needed to amend the model of the atom. So the scientific model has changed if the experimental results show that this model was wrong. So a new scientific model is created when which can explain the experimental results. So like we mentioned before, the scientific model is the idea or theory used to explain observations and data made in experiments. Now, the second model was Thomson's plum pudding model of the atom. So Dalton's model of the atom was no longer acceptable because there was now something inside the atom, the electron. So Thomson believed the atom was made of positively charged matter with negatively charged electrons scattered through like plums in plum pudding. So the plum pudding model was the first attempt at redefining what the atom looked like. So in the theory of the plum pudding model, Thomson realised that the plums, or in this case the chocolate chip with the negative electrons, and the solid filling, either being the pudding filling or the muffin filling, was the positive charge. Now, in this idea, the atom was still completely solid. There was no space in the atom. So please, in Thomson's plum pudding model, do not refer to protons in it because it's not. We did not discover the proton yet. It's just positive charge. Now, it's also important to note that in the plum pudding model, there's no space in the atom. Now, this model was used to explain the experimental observations of electrons because it also explained why the atom is uncharged electrically, because in the plum pudding model you've got negative electrons and positive charge. So with new observations and data we came up with the plum pudding model, but because remember, a new model is always proposed if we need to explain observations and data. Then Ernest Rutherford came along and tested out this particular model. He did this by carrying out the gold foil or Rutherford scattering experiment. So what Rutherford did is he got a layer of gold foil 1 atom thick. He then fired alpha particles at this gold foil. Now, the alpha radiation was a new discovery of science at this point. It was a type of radiation emitted from nuclei which increases the stability of the nucleus. Now again, alpha radiation is ionizing, which means it can ionize your DNA, which can mutate your DNA and can lead to cancer. Now, an alpha particle is 2 protons and 2 neutrons, so it's a helium nucleus, and therefore it has a positive charge of +2. Now, it's important to note that we did this experiment in a vacuum chamber because the alpha particles would be ionized if there was air in between the alpha particle and the gold atoms, so the alpha particles would stop in about 5 centimeters of air. Now, if there was no vacuum chamber, the alpha particles would not even reach the gold atoms. So what Rutherford did is he placed an alpha particle detector on the other side of the gold atoms, and he moved the angles at which the gold particles were fired at the gold foil and measure what happens to the alpha particles after they pass through the gold foil. So he moved around his alpha particle detector. Now, Rutherford expected these fast-moving alpha particles to smash straight through the atom as proposed by the plum pudding model. Now, Rutherford did actually find that most alpha particles pass straight through the gold foil like expected. Now, this actually happened because the gold atoms are predominantly empty space. So the first conclusion Rutherford made was the atom is mostly empty space. Now, some alpha particles deflected away from the nucleus. Now, the nucleus also slightly records this movement, but this is actually a much smaller effect because the nucleus is much more massive than the actual alpha particles, so it's something called the conservation of momentum. Now, this deflection happens because there must be a positive charge in the atom, because the positive charge of the atom and the alpha particle repel each other. So we then concluded the nucleus of an atom is positively charged. And then finally, 1 in 10,000 alpha particles reflect backwards off the atoms. Now, they don't literally reflect, they repel backwards without touching the gold atoms, which can sometimes be referred to as backscatter. Now, this occurs due to the large repulsion between the positively charged alpha particles in the nucleus, and this will only occur when the alpha particles will directly contact with the nucleus. Now, because only a small number do this, the nucleus cannot be that large. Now, it's better to talk about sizes in terms of a nuclear radius compared to atomic radius. So this showed us that the nucleus must have a much smaller radius than that compared to the atom. So the radius of the nucleus is much smaller compared to the radius of the atom. So remember, most alpha particles deflect through, some deflect away from the atoms, and some reflect backwards off the atoms when they carry out this experiment. Now, we compared the results with expected results compared to the plum pudding. Now, like we said before, if the experimental results do not fit the old model, then we had to come up with a new model displaying these results. So Rutherford devised a new scientific model which explained the new observations of this experiment. So observation 1, most of the alpha particles pass straight through the gold atoms. The atom is mostly empty space. Most of the alpha particles are reflected when they pass near the center of the gold atom. There is a positively charged nucleus, and about 1 in 10,000 alpha particles are reflected by more than 90 degrees. So the diameter of the nucleus is about 10,000 times smaller than the diameter of the atom. So to explain these results, this is the new atom that was proposed. Inside every atom is a nucleus, and the nucleus contains all of the mass of the atom. This nucleus contains all the positive charge of the atom. This nucleus is extremely dense. The nucleus contains most of the mass, yet it has a radius 10,000 times smaller than the atom. So the results from the alpha particle scattering experiment led to the conclusion that the mass of an atom was concentrated at the center, which was a nucleus, and that this nucleus was charged. So this nuclear model replaced the plum pudding model. Now, Niels Bohr then adapted the nuclear model by suggesting the electrons orbit the nucleus at specific distances. The theoretical calculations of Bohr agreed with experimental observations, so this amended the model. Now, later experiments led to the idea of positive charge of any nucleus could be subdivided into a whole number of smaller particles, each particle having the same amount of positive charge, and the name proton was given to these particles. Now, the experimental work of James Chadwick provided evidence to show the existence of neutrons within the nucleus, and this was about 20 years after the nucleus became an accepted scientific idea. So this led us to the model of the atom which we're familiar with today, the nuclear model. The atom has a positively charged nucleus. It has a very small radius compared to the atomic radius. The atom is mostly empty space, and the nuclear model was amended when Chadwick discovered the neutron, and the neutron was found in the nucleus. Now, the electron structure was amended when Bohr deduced the electron energy level structure. So we can actually summarize the ideas of the Rutherford scattering experiment by considering the conditions of the experiment, the results of the experiment, and therefore the conclusions of the experiment. So let's now look at the next section of this particular topic, which is radioactive decay and nuclear radiation. So nuclear radiation is produced when unstable nuclei emit particles or energy, so therefore change to become more stable. Now, this process is called nuclear decay, and a nucleus can do this by one of three methods, by either releasing alpha radiation, beta radiation, or gamma radiation. So what happens is an unstable nucleus wants to become more stable, and it does this via nuclear decay. So to become more stable, it will give off radiation, which we then call a decay. So it's a decay as the nucleus is releasing either particles or energy to become more stable. So it's an event that increases nuclear stability. So when radiation is given off, the nucleus will become more stable. So this process will only involve the nucleus of the atom. So don't use the phrase atom when considering radioactive decay. So radiation is the energy or particles given off by the nucleus to shed this excess energy, which we can also called radioactive emission, and there are three types of radioactive decay an unstable nucleus can undergo. So therefore the radiation can take three forms depending on the unstable nucleus, but all the radiation always originates from the nucleus of the atom, and those are either alpha radiation, beta radiation, or gamma radiation. Now, these types of radiation are called ionizing radiation. This is because the particles ionize the other particles they encounter, so the radiation can knock electrons out of atoms. So alpha radiation is the release of an alpha particle, and an alpha particle, like we can see, is consisting of 2 protons and 2 neutrons, so it has a positive charge. So it means the alpha particles would deflect to the south pole of a magnet or the negative of an electrical field. Alpha particles have a relatively large mass, which makes them highly ionizing, so they can only travel about 5 centimeters in air. So this means they're absorbed by materials like paper or anything denser. So alpha particles are only emitted from the nucleus of an atom. So we can summarize summarise the properties of alpha radiation with the following slide. Now please remember, alpha radiation comes from the nucleus of an atom. So here we can show the idea of what's going on in alpha radiation. So that's what's taking place when this alpha decay takes place. Now a beta particle is emitted when a neutron in the nucleus changes into a proton and releases a negative charge in the fast moving electron. So beta radiation is an electron. Beta particles have a negative charge, so it means they deflect towards the north pole of a magnet or the positive of an electrical field. Now beta particles have a mass smaller than an alpha particle, so they would deflect more in a magnetic or electrical field than the alpha particle, but that means they are moderately ionizing and would travel about 1 meter in air. They will be absorbed by an aluminium sheet about 5 millimeters thick or a lead sheet about 2 millimeters thick or anything denser. Now beta particles must come from the nucleus, which we can all summarize the properties of beta particles with the following screen of information. Now again, remember, this radiation must come from the nucleus of an atom. So here is a summary of the beta decay process. Now, gamma radiation is when after a nucleus has emitted an alpha or beta particle, it may have too much energy, so we say it's in an excited state. So to get rid of this energy, it can emit a pulse of very high frequency electromagnetic radiation called a gamma ray. So gamma radiation has no charge, it is only energy. So it does not deflect in either direction in a magnetic or electrical field. It has no mass, it is only energy, so it's not very ionizing, and it can travel for an unlimited distance in the air. So gamma radiation can never be completely absorbed by a material, but it can be reduced by thick lead or concrete or anything denser. Now gamma radiation must also come from the nucleus, so we can summarize all these topics in the following slide. Now again, all radiation comes from the nucleus of an atom, so again we can summarize the properties of gamma radiation. Now we can then look at these ideas in the concept of nuclear equations. So in mathematics we can represent change by an equation, which you can also do in chemistry as well. Now in mathematics you use an equal sign because there's no passage of time, but we use an arrow sign in chemistry because there is a passage of time, there is a before and after. Now in chemistry we balance equations as the total number of atoms must be conserved. Now the word conserved in this instance means stay the same. So in chemistry we balance the equations as the total number of atoms before must be the same as the total number of atoms after in a reaction. Now in physics we can also use equations to show the radioactive decay process, which we call the nuclear equation. Now in physics we've got to be aware the number of protons and neutrons are always conserved in nuclear decays. So the number of protons and neutrons is the same before a nuclear decay as it is after. So this means the mass number and the atomic number is the same before a nuclear decay as it is after. So in a question you should use these facts to complete the decays for alpha, beta and gamma, and also recognize if it is either alpha, beta or gamma. So you can consider what happens before a decay and after a decay. Now remember, this is not a chemical equation as it only concerns nuclei, because only the nuclei decay in nuclear decay. So we can represent, like we said before, a nucleus of an atom with A as the atomic mass and Z the atomic number. So in any nuclear decay, the total atomic mass before equals the total atomic mass after. So in this instance, 28 before equals 28 after. And again, the total atomic number before equals the total atomic number after. So in this case, 15 before equals 15 after. So mass is always conserved in a nuclear decay, and the number of protons and neutrons are always conserved in a nuclear decay, which is a fundamental concept found in chemistry. So then now let's have a look at what's going on in the alpha decay process. So alpha decay causes the nucleus to lose 2 protons and 2 neutrons, so it causes the atomic mass to decrease by 4 and the atomic number to decrease by 2. So this means the nucleus after decay has changed element as there's a different number of protons. So alpha decay is a process of transmutation as you've made a new element. So it's very important to note that alpha decay is transmutation as it produces a new element after the decay process. Now the alpha particle can be given the symbol 4,2 or He, 4,2. Now alpha decay causes both the mass and the charge of the nucleus to decrease. Now like we said before, an alpha particle can be considered a helium nucleus which is emitted with exactly the same amount of kinetic energy for each event in our universe. So in alpha decay, the atomic number decreases by 4, mass number decreases by 4, the atomic number decreases by 2, so a new element is formed 2 places lower in the periodic table than the original element. So as we said before, the atomic mass numbers decrease by 4, the atomic numbers decrease by 2, so it produces a new element as there's a different proton number in the nucleus. So as we said, alpha decay causes both the mass and the charge of the nucleus to decrease. So we can then summarize the properties of alpha decay with the following slide of information. Now in beta decay, a neutron changes into a proton plus an electron. The proton stays in the nucleus whilst the electron leaves the atom with high energy as a beta particle. So the beta decay causes the nucleus to turn a neutron into a proton and an electron. As we said, the proton stays in the nucleus and the electron is fired out of the nucleus at a very high speed. So the atomic mass stays the same whilst the atomic number is increasing by 1. This happens as the numbers are conserved, so it means that the nucleus after decay has changed element as has the different number of protons. So what we can say is beta decay is another example of transmutation. Now the beta particle is represented by beta 0-1 or E0-1. Now beta decay does not cause the mass of the nucleus to change, but it does cause the charge of the nucleus to increase. So this occurs because the neutron wishes to turn into a proton, as the proton is slightly smaller and therefore is slightly more stable than compared to a neutron. So let's clarify what beta decay is. The atomic mass stays the same, the atomic number increases by 1, so a new element is formed that is one place higher in the periodic table than the original element. So as we said before, the top number, the atomic mass number, stays constant, but the atomic number increases by 1. So the beta decay does not cause the mass of the nucleus to change, but does cause the charge of the nucleus to increase. So a new element has been formed as the proton number has changed, but so therefore we can summarize all the information of the beta decay in the following slide. Now in gamma decay there is no change in the makeup of particles, the nucleus just loses energy. So gamma decay causes the nucleus to release only energy. It causes the atomic mass and the atomic number to remain unchanged. So the nucleus does not change element after nuclear decay. Gamma decay is not an example of transmutation. Gamma decay is a relaxation of a nucleus as the protons and neutrons change their way they're arranged in the nucleus. Now we can represent gamma rays as gamma 0, 0. So the emission of a gamma ray does not cause the mass or the charge of the nucleus to change. So in gamma decay, the atomic number and the atomic mass number have not changed in this decay, so the proton number is unchanged, so the element of the nucleus is unchanged. So the emission of gamma rays do not cause the mass or the charge of the nucleus to change. And the next thing we're going to cover is half-life. So when an unstable nucleus decays and becomes stable, the unstable nucleus can release radioactive emissions. So there are two steps to this nuclear decay. The nucleus decays and becomes stable, but it also releases radioactive emissions. Now we can use either of these steps to measure nuclear decay. So the first way you can measure decay is via activity, which is how many radioactive nuclei decay and become stable every second. And we measure this in becquerels, which is 1 becquerel is 1 radioactive nucleus decaying every second, which was named after the scientist who discovered the concept of radioactivity. The second way we can measure radioactivity is the count rate, which is the number of radioactive particles detected per second by a detector, and count rate is measured in per second. Now the detector needs to be the same distance away from a radioactive source to gain accurate results for a count rate. Now physicists can use either measurement depending on the ease of the measurement. Now the activity and count rate can differ as each decay might produce more than one emission, or the detector might not pick up all the radioactive emissions given out, or the radioactive emission can pass through the detector without being registered. So we've got to consider activity and also count rate, and use either quantity to measure the radioactivity of a source. In half-life can be measured by the change in activity or count rate of a source, and either can be used in physics. So we can measure radioactive decay by looking at the activity or count rate of a sample, which can lead to the half-life of a substance. So the half-life of a radioactive isotope is the average time it takes for the number of radioactive nuclei of the isotope in the sample to half, or for the count rate to fall, or the activity of the isotope to fall to half its initial value. So for example, go from 600 counts per minute to go to 300 counts per minute. Now all radioactive substances have a measured half-life, and it's very similar to rolling a dice. An unrolled dice could be considered an unstable nucleus, and a rolled dice for one particular side could be considered a stable nucleus. Now you cannot say whether an individual dice will roll a particular number, so you can't say whether an individual nucleus will decay. So we say radioactive decay is a random event, and also you cannot influence whether an individual dice will roll a particular side, so you can't influence whether nuclear decay will occur. So radioactive decay is a spontaneous process. Now you can't predict how many dice will roll a 6 on average, like how many times you can predict how long it would take for the half of the unstable nuclei to become stable, which we call half-life. Now, the half-life for a particular radioactive isotope is constant, but we always take the half-life as an average time, as radioactive decay is a random event. So radioactive decay is constant as each radioactive nucleus has the same chance of decaying as each other. So the random nature of radioactive decay requires repeated readings to be made over a long period of time. Now we can determine the mass of the radioactive isotope left after a radioactive decay from the half-life via the following formula. The mass of radioactive nuclei remaining is equal to 0.5 to the the power of the number of half-lives that are passed times by the initial mass, or you could write it out as the initial mass over 2 to the power of the number of half-lives passed. Now this is the equation, the same equation written in different forms. Now you can also do this for the mass number, the activity, and the count rate due to nuclear decay. So again, this is a formula you've got to be able to remember for your examination, whether it be the mass, whether it be the count rate, or whether it be the activity. So for example, a particular radioactive isotope has a half-life of 6 hours. A sample of this isotope contains 60,000 radioactive nuclei. Calculate the number of radioactive nuclei of this isotope remaining after 24 hours. So firstly, you work out how many half-lives there have been, and there's been 4 half-lives because there have been 4 half-lives in 24 hours. So you do your initial value, 60,000 divided by 2 to the power of the number of half-lives, so 2 to the power of 4, so it's 3,750. Now the activity, count rate, and rate of nuclei can be plotted against time, and the following graph can be found. So what happens is this graph occurs as the nuclei radioactive decay over time and become stable. Now this graph is an example of an exponential relationship. Now an exponential relationship is a relationship where the rate of change is constant as a percentage of the value. So in radioactive decay, the time taken to fall by 50% is constant. So this graph is an exponential decay because the rate of change is always decreasing. Now to work out the half-life, what you would do is you draw 2 lines on your graph where the activity is half of each other. So for example, one line where the activity is 200 and one line where the activity is 100. You then extrapolate the lines downwards to find the corresponding time, and the difference between the 2 times is the half-life. So for example, you could do 8,000, look down for the time, 4,000, look down for the time, and the half-life is the time taken between the first activity and the second activity measured. So we'll always try and use rounded numbers to derive these values as it's easier to measure. So we can think of those ideas when working out our half-life. Now you can also do this if it's the mass of radioactive isotope or the count rate used. So you can see on the screen the idea of how you calculate half-life. Now you should always take it over a number of values and calculate a mean, as is to minimize the random nature of radioactive decay. Now remember, in theory, radioactive decay curves never fall to 0 because there's always some radiation present in any environment you take measurements in. Now in theory, the half-life remains fixed, so the value for half-life calculated should be the same no matter what 2 values are used in this method, but in reality it will vary slightly because radioactive decay is a random event. So it's best practice to take multiple half-lives and then find an average, as you can see in the following example. So there's just a slide summarising what we've just covered in how you can derive the half-life from a graph. Now we're also now going to look at radioactive contamination. Now there's been many scientific published reports on the impact of radioactive emissions. Now it's important for scientists to share the impact of radiation on humans because the facts can then be checked by peer review and seen if they are reproducible. So to understand the impact of radiation on humans, we've got to understand what the word radiation means. Now the radiation in this idea we're going to look at is radiation is the nuclear radiation released by unstable nuclei as it becomes more stable. Now gamma radiation is actually both nuclear radiation and electromagnetic radiation. Now electromagnetic waves or nuclear radiation which can damage human cells is called ionizing radiation. Now certain types of electromagnetic waves can be ionizing radiation, but all types of nuclear radiation is ionizing radiation. Now ionizing radiation can have a damaging impact to human health. So what is actually the process? So when radiation hits an atom, it can knock electrons out of an atom. The atom becomes an ion, and this process is called ionization. So the release of an electron from its structure turns an atom into a positive ion. The larger the radioactive emission, the more likely it is to ionize an atom. So the larger the radioactive emission, the larger the ionizing power. So alpha particles have the highest ionizing ability and gamma waves have the lowest ionizing ability. Now alpha particles are likely to knock electrons out of the atom as they are so massive, whilst gamma waves are unlikely to knock electrons out of the atom as they have no mass. Now ionization can happen to your DNA in your cells. So ionization can cause your DNA to mutate, which can lead to cancer. So ionization of atoms can lead to mutations in DNA, which can lead to cancerous tumours forming. Now all ionizing radiations can cause cancer to develop, however it's down to chance. So there's always a chance of this event occurring. So all ionizing radiation has some chance of causing cancer in humans, however the likelihood of this happening varies. So the chance of ionizing radiation giving humans cancer is measured in sieverts. So an exposure of 1 sievert gives a human a 5% chance of getting cancer. So 1 sievert will cause illness if absorbed all at once, and 8 sieverts will result in death even with treatment. segment. So the value of sieverts depends on the dose of radioactive emission and the type of radioactive emission. So the value of sieverts also depends on the part of the body where it hits. Now a large dose of alpha parts will give a large sievert value to a human, so it gives a greater chance of ionization in cancer. Now when an object is exposed to ionizing radiation, we say it is irradiated, because irradiation is the process of ionizing radiation passing through an object, and it leads to the possibility of ionization, mutation, and cancerous tumors developing. So examples of irradiation can include X-ray imaging and radiotherapy. So if an object is irradiated, it does not become radioactive, because once the ionizing radiation has passed through the material, there is no longer any effect. Now materials can be contaminated if they are coated in unwanted radioactive nuclei. So these nuclei will decay over time and release nuclear radiation because they're becoming more stable. Now when this occurs, the radioactive nuclei emit radioactive emission like gamma, alpha or beta. Now in this example, the material is contaminated, so the radioactive nuclei on the material can release radiation which could harm the object. Now once the material has become contaminated, it is now radioactive until all the unwanted nuclei have been removed. So contamination of a material can lead to long-term irradiation, and this would happen at a very close distance. So it means a contaminated object would receive a high dose of radiation, which would increase the chance of harm, because there's very little shielding of any radiation, which increases the chance of harm. So contamination leads to a greater chance of cancer development compared to irradiation. Now many examples of large-scale rate of contamination have been when nuclear power stations have exploded, such as the Fukushima power station 2011. So this is contamination, as the radioactive nuclei are not wanted on the topsoil around the Fukushima power plant. Now it's important to note that contamination will only occur if you have unwanted radioactive nuclei on a particular object, and it was also the case when the nuclear power station exploded in Chernobyl in 1986. So it's very important we understand what contamination is. So irradiation is when an object is exposed to ionizing radiation but the object itself does not become radioactive. Contamination is the unwanted presence of radioactive nuclei on a material. These decay and give out radiation, but the object does become radioactive. Now it can lead to ionization, mutation and cancer in humans. So all ionizing radiation is dangerous, and all ionizing radiation has the chance of causing cancer. So increasing your dose of radiation increases the chance of cancer, which we measure in sieverts like mentioned before. Now, it's important to know that the dose of radiation is normally always due to the background radiation, which is lower than much levels, which can typically lead to cancer. However, there's always some chance that background radiation can cause cancer. Now, the dose you receive from your background radiation varies on your location and your occupation that you have. Now, many scientists will work with ionizing radiation, such as radiographers, nuclear power station workers, aviation engineers. Now, this occurs because they've got an increased exposure to cosmic rays as the higher from the atmosphere for longer periods of time. Now workers who use ionizing radiation should reduce their exposure by keeping as far away from as possible from the source of radiation. So never handle radio sources directly and point them away from the body. So use tongs to prevent contamination and minimize irradiation. You should spend as little time as possible in areas with a high background of radiation. So workers are only allowed to spend a small amount of time in areas with radioactive materials. So this will reduce irradiation. And precaution 3, shield yourself from radiation with lead or concrete barriers. So here the source is encased in lead, leading to reduced emission of ionizing radiation, as lead will block alpha and beta radiation and reduce the effect of gamma radiation. So this will reduce the effect of irradiation. Now many hospitals have lead-lined walls, which reduces irradiation for patients and visitors. So you've got to keep away as far as possible from a source of radiation, spend as little time as possible in areas of high background radiation, and shield yourself using either concrete or lead barriers. Now even with these procedures in place, people who work in ionizing radiation will receive a dose of radiation, and this must be monitored to ensure it's not a large dose. So people wear badges which will monitor the exposure to radiation, and if a person receives a large dose of radiation while they're working, their badge will change colour. So let's summarise what we know so far about atomic structure. The basic structure of an atom is positively charged nucleus comprised of both protons and neutrons surrounded by negatively charged electrons. The radius of a nucleus is about 10,000 times smaller than that of an atom. Most of the mass of an atom is concentrated in the nucleus. Now in the atom the number of electrons is equal to the number of protons, and atoms have no overall electrical charge. All atoms of a particular element have the same number of protons, and the number of protons in an atom is called its atomic number, and the total number of protons and neutrons in an atom is called its mass number, which can represent with the following example. Now, atoms of the same element can have the same number of protons but a different number of neutrons, and they are called isotopes. Now, atoms can turn to a positive ion if they lose one or more outer electrons. Now, new experimental evidence can lead to a scientific model being changed or replaced. So before the discovery of the electron, atoms were thought to be tiny spheres that could not be divided. The discovery of the electron led to the plum pudding model of the atom. The plum pudding model of the atom suggests the atom is a ball of positive charge with negative electrons embedded in it. The results from alpha particle scattering experiments led to the conclusion that the mass of the atom was concentrated at the centre, and that this nucleus was charged. This nuclear model replaced the plum pudding model, and Niels Bohr adapted the nuclear model by suggesting that the electrons orbit the nucleus specific distances, and the theoretical calculations agree with experimental observations. Now, later experiments led to the idea of positive charge of any nucleus could be subdivided into the whole number of smaller particles, each particle having the same amount of positive charge, and the name proton was given to these particles. The experimental work of James Chadwick provided the evidence to show the existence of neutrons within the nucleus, and this is about 20 years after the nucleus had become an accepted scientific idea. You should be able to explain why the new evidence from the alpha particle scattering experiment led to a change in the atomic model, and the difference between the plum pudding model and the nuclear model of the atom. Now, some atomic nuclei are unstable, so the nucleus gives out radiation as it changes and it becomes more stable. This random process is known as radioactive decay. Activity is the rate at which the source of unstable nuclei decay, and the activity is measured in becquerels. Count rate is the number of decays recorded each second by a detector, and the radiation to emit could be alpha particles, 2 protons, 2 neutrons, beta particles, an electron, or gamma rays, an electromagnetic radiation, or just a simple nucleus. Now, you should know the properties of alpha, beta, and gamma rays, and you should know the penetration, their range, and their ionizing power. Now, nuclear equations can be used to represent radioactive decay, such as the symbols for alpha and beta radiation. Now, the emission of different types of nuclear radiation may cause a change in mass or charge of the nucleus. So, alpha decay causes both the mass and charge of the nucleus to decrease, but beta decay does not cause the mass to change, but does cause the charge to increase. Now, you then should be able to work out the symbols of alpha and beta decay, and the emission of gamma rays does not cause the mass or charge of the nucleus to change. Radioactive decay is random, and the half-life of a radioactive isotope is the time it takes the number of nuclei of the isotope in a sample to half, or the time it takes for the count rate or activity from a sample containing the isotope to fall to half its initial level. You should be able to explain the concept of half-life and how it is related to the random nature of radioactive decay, and should be able to determine the half-life of a radioactive isotope from given information, including carrying out a calculation. Now, radioactive contamination is the unwanted presence of materials containing radioactive atoms on other materials. The hazard from contamination is due to the decay of contaminating atoms. The type of radiation emitted affects the level of hazard, and irradiation is the process of exposing an object to nuclear radiation. The irradiated object does not become radioactive, so you should be able to compare the hazards associated with contamination and irradiation, and understand that suitable precautions must be taken to protect against any hazard that the radioactive source used in the process of irradiation may present. Now, you should also understand that it's important for the findings of the studies into the effects of radiation on humans should be published and shared with other scientists so their findings can be checked by peer review. So I hope you've enjoyed today's revision session on atomic structure, which is part of the GCSE Separate Science course in physics. Thank you very much for watching, and as always, have a lovely day.